Okay, so we are back again, right. So next is actually equations of motion, right, and this is the last part of this course, right. So next is the equation of motion for the section 2. So it will be 2h2 d dt of delta omega 2 is equal to TLPA plus K23 delta 3 minus delta 2, then minus K12 delta 2 minus delta 1 minus d2 delta omega 2, because these are the input torque, right, and this is your equation of motion. And similarly, your d delta 2 by dt will be delta omega 2 omega 0. This type of equation already we have derived, and here you are considering separate several subsection. So you have to write this your what you call equation of motion like this, right. So these two are input torque, then you make it minus K1 to delta 2 minus delta 1, this is output torque, and this was damping minus delta 2 into delta omega 2, right, d2 into delta omega 2, and this is your d delta t upon dt is equal to delta omega 2 omega 0, right. Now equations of the complete rotor system shown in figure 1 may be summarized. Now similarly, you have your in figure 1 we have section 1, section 2, section 3, section 4 and section 5. So similarly, one after another you proceed, and the way I showed the first 2 sections, 3 sections, similarly you can write down the equation from the inspection, right. So for the your what you call for therefore for generator, now we summarize this, now rewriting this equation for generator 2h1 d dt of delta omega 1 is equal to K12 delta 2 minus delta 1 minus T minus d1 delta omega 1. Now d dt of delta 1 delta omega 1 into omega 0. Similarly, for LPA section 2h2 d dt of delta omega 2 is equal to TLPA plus K23 delta 3 minus delta 2 minus K12 delta 2 minus delta 1 minus d2 delta omega 2, and d dt of delta 2 is equal to delta omega 2 omega 0. These two we have seen that how to make it here and here also how to make it. Now we are summarizing this. Similarly, for section 3 same way we will write 2h3 which will be d dt of delta omega 3 is equal to, this is the input torque, right, that is TLPB, that is the section B, that low pressure turbine, right, TLPB plus K34 into delta 4 minus delta 3 minus K23 delta 3 minus delta 2 minus D3 delta omega 3, this is for the section 3, right, and d dt of delta 3 is equal to delta omega 3 into omega 0, right. Similarly, for intermediate pressure, just from your inspection you can write that 2h4 d dt of delta omega 4, only their inertias are different, right, because you are considering your what you call different sections, is equal to TIP plus K45 into delta 5 minus delta 4 minus K34 delta 4 minus delta 3 minus D4 delta omega 4, and d dt of delta 4 will be delta omega 4 into omega 0, right. So this is your what you call that's intermediate section. Now in your then high pressure, that is intermediate pressure, that is high pressure. Now for high pressure, this section 5, it is 2h5 d dt of delta omega 5 is equal to THP, that was the input torque, minus K45 into delta 5 minus delta 4 minus D5 delta omega 5. This is for the high pressure portion, section 5, and d dt of delta 5 will be delta omega 5 omega 0. This is how we have to represent that each section, right. So now we will take one example, right, we will take one example. The data applicable to a 5 mass torsional model, that is your figure 1, right. Figure 1 also we have considered 5 mass of 960 MVA, 24 kV and 0.9 power factor, 1800 rpm, 4 poles, 60 hertz. So it is 1800 rpm, right. Nuclear unit with a static exciter is as follows. So these are the data given, right. So in this example, only one thing I will not calculate for you, I will give the final answer, but I request you to compute that one, right. So that is there are 5 sections. So 1, 2, 3, 4, 5. So there is different mass is there. So 1 is generator, 2 is the low pressure turbine, the section A, section B, that is LPB, and your intermediate pressure, that is LPC, and this is high pressure, right. So power fraction, generator is nothing, but other turbine fraction it is 0.24, 0.24, 0.24, and this is high pressure side is 0.28. If you add all, it will be 1, because we are representing is fraction, that is per unit, right, fraction. And this is your moment of inertia in pound feet square. It is a huge figure, it is given, right. So, for example, this is 11 lakh 14,382 like this. So, these are huge data. So, that is pound feet square is given, and these are the shaft section. This is generator, this is actually your generator to LPS. So, this is actually section 1 to section 2, right, and this is section 2 to section 3, this is section 3 to section 4, and this is section 4 to section 5, right. So, 1 to 2, 2 to 3, 3 to 4, and 4 to 5. So, there are 4 sections, right, 5 masses, so 4 sections, so 4 shaft, right. And your these are your what you call, these are the stiffness, that is given pound feet per radian. So, it is a huge I mean these figures are very large, right, but this stiffness is given that pound feet per radian, but we will convert it to your what you call that kg meter per radian, and here also we will make your kg meter square, right. So, you have to find out that determine the inertia constant H in megawatt second upon MVA, that is in second, right, for each of the 5 masses, and the stiffness K in per unit torque per electrical radian for each of the 4 shaft section, that we have to determine. And B, compute the steady state value of torque transmitted by each shaft section and the angular displacement between the generator and the high pressure turbine section when the generator is operating at rated output, right. So, these two things. Now, solution. The moment of inertia of the HP section rotor mass, that is mass 5, right, that is what you call that high pressure section. We know this transformation for your what you call while doing your synchronous machine chapter, right, that it is given inertia is given LV feet square into 1.356 upon 32.2. This already we have done it. So, here this inertia is given for section 5 this much, it is pound feet square, that is 2,25,240 pound feet square into 1.356 upon 32.2. So, that is actually 9,485.3 kg meter square, right. Similarly, the corresponding inertia constant is this, also we have done it, this also we have done it for your synchronous machine topic, right. So, somewhere we have done it. So, this is for each section we are writing, but general formula is half j 2 pi into revolution per minute RPM upon 60 square into 1 upon volt ampere rating. This also we have done it. So, if you substitute all these values half into j, so j value just now we have got this one, this is the j value, right, into 2 pi RPM was given in the data, that is 1800 divided by 60 square into MVA was given 960 MVA, we have to convert it to volt ampere. So, 1 upon 960 into 10 to the power 6, right. Therefore, H5 will become 0.1755 megawatt second per MVA, that is nothing but 0.1755 second, right. So, this is inertia for the section 5, that is your high pressure turbine section, right. Similarly, similar way you calculate that inertia for other 4 masses, the LPC, LPB and LP as given in figure 1 and the generator, right. If you follow the same procedure, you will get, these are actually you will get, units are not written, it is all are second actually, all are second, all are second, all are second. Sometimes we write that your megawatt second per MVA, right. So, all are second. So, if you follow this and calculate, you will get your what you call these values H4, H3, H2 and H1 similar way. That is why your, that is why other these calculations, only one calculation shown. So, other you can easily compute. So, calculations are not shown, that is why, right. So, now the torsional stiffness of the shaft between the HP and LP turbine section is that K45 is actually is equal to 1.356 K, right. Therefore, it is 1.356 and K is given because huge data is given for section 4 5, right. So, it will be 1.33530219, right. So, it becomes actually huge figure Newton meter per mechanical your what you call radian. So, all these things your what you call that the way we have converted your what you call, that is your inertia, that is 1.356, this we have derived earlier. Similarly, for stiffness also you try to do little bit yourself, right. Same thing we have made it in synchronous machine chapter, but stiffness was not there. Stiffness was not there, but same philosophy you follow to change the unit, because it was given in British unit, you convert it to that MKs, right. So it is becoming K45 will become this much of Newton meter per mechanical radian. Therefore, if you make it per unit, it will be K45 per unit torque per electrical radian will be whatever you have got it divided by VA base into 4 omega 0 upon PF square. This we have derived in the beginning, right, in the previous lecture. This one was made it, right. So, K45 per unit torque per electrical radian, and this one just derived in the previous lecture. If you put it, it will become actually 17.78 per unit torque per electrical radian. PF is equal to 4 and 60 hertz, omega 0 is 377, right. Therefore, stiffness value for other similar way, you find out the stiffness values for other sections, right. So, LPC to LPB, LPB to LPA, that is 3 to 4, 2 to 3 and 1 to 2. So, you will find K34 will be 27.66, all are in per unit, right. That is per unit torque per electrical radian. K23 will get 31.31 and K12 will get 37.25, right. Just I did not show all this calculation, but only one calculation is shown. Similarly, others you can easily calculate, right. Now, part B, the air gap torque T in per unit, your what we call a 960 MVA base is 0.9. This one, this is you just see it, right, from where it has come, right. So, the torque developed by the different turbine sections are, that is your this one TLPA is equal to TLPB is equal to TLPC, because all are 0.24. There it was given your what you call that in the data. I am going to the data, that it was given that all 0.24, these three are equal, multiplied by 0.9. So, these three are equal, right. So, here it is, right. So, it is 0.24 into 0.9. So, 0.216 per unit for 3, right, and for your what you call the torque transmitted your by the shaft section between the generator and LPA is the T12 is equal to TE is equal to 0.9, right, this is 0.9. So, therefore, the angle by which LPA rotor leads the generator rotor is the delta 21 is equal to delta 2 minus delta 1 is equal to T12 upon K12, because we know T12 is equal to K12 into delta 2 minus delta 1, right. Therefore, this is your what you call the delta 21 will be then 0.9 divided by 37.25. So, it will become 0.02416 your what you call electrical radian, right. The torque transmitted by the shaft between LPA and LPB turbine section will be similarly that your T23 will be T12 minus TLPA, right, is equal to this much minus 0.216, it will be 0.684 per unit, right. Hence, your delta 32 will be delta 3 minus delta 2 is equal to T23 upon K23. So, T23 is known, K23 also we have computed before. So, it will become 0.02185 electrical radian, although this variation if you look it is very small, but it has some meaning, right. Similarly, delta 3 will be delta 4 minus delta 3 is equal to T34 upon K34, that is your 0.684 minus 0.216 upon 27.66. So, that is actually 0.01692 electrical radian, right. And delta 54 will become delta 5 minus delta 4 is equal to T45 upon K45. So, delta 54 will become 0.252 upon 17.18, because all stiffness have been computed before. So, it is 0.01417 electrical radian, right. Thus, the HP section rotor leads the generator rotor by delta 5 minus delta 1, because this delta 5 as this delta 54 means it is delta 5 minus delta 4, right. Then plus delta 43 means delta 4 minus delta 3, plus delta 3 means delta 3 minus delta 2, plus delta 2 minus delta 1. So, delta 2 will be cancelled, right, delta 3 will be cancelled, delta 4 will be cancelled. So, finally, it will be delta 5 minus delta 1. right. That is why we are just what we are doing is that you delta 5 minus delta 1 is that you add all, right. So, that is nothing but delta 5 minus delta 1. If you add all, you will get 0.0771 electrical radian, that is 4.42 your what you call electrical degrees. This is electrical degrees, it is converted to degrees, right. So, that is the problem what is asked, right. After this, so with all these things, your subsynchronous, your oscillations, all these things, just little bit we have touched, right. It is basically a vast chapter. So, after this, that whenever we go for your the stability studies or any other control thing, there are limiters is there, right. So, little bit we will touch limiter, that how actually mathematically it works, right. So, for example, Windup and non-Windup limits. So, these two things. So, now in the modeling of your what you call excitation system, it is necessary to distinguish between Windup and non-Windup limits. Although modeling for excitation part, we have no time to do that. So, we could not touch it, only little bit we have talked, but we could not touch it, right. But not only that, in other control part also sometimes we use the limiter, right. So, Windup and non-Windup your what we call limits. Such limits are encountered with integrator blocks, single time constant blocks and lead lag blocks. So, this thing we will see that how actually mathematically it works, representation. So, first you see that your what you call it is your what you call Windup limit. So, representation, this is input is u, this is an integrator, output is v, right, but it is restricted to Lx to Ln and this output is y. Now, how it behaves when we put this symbol, actually how it behaves. So, first system equation will be dV, this is V actually, actually here I have written dV by dt. So, this is actually V, right, I have written like this, but this is actually dV by dt. So, dV by dt is equal to u, right. So, now system equation actually it is dV by dt, first you make it u, the dV by dt is equal to u. Now, how limiting action will be there, this is for integrator and you are putting a limit, right. Lx and your what you call Ln, that upper and lower bound. So, limiting action when V, this output lying in between Ln and Lx, that is your constant is not violated, this not violated, then y is equal to V, that is pass, right. So, V will pass if V is lying between Ln and Lx, right, and dV by dt is equal to, the constant is dV by dt is equal to u, right. Now, if V greater than Lx, I mean if V greater than Lx, you set y is equal to Lx. So, you set y is equal to Lx, right, and if V less than equal to Ln, you set y is equal to Ln, right. So, this is actually limiting action and this is figure A, that is integrator with Windup limits, this is we call Windup limits, right. Next is your representation non-Windup limits, right. In this case, we mathematically your block diagram representation is like this. This is input is u and output is y, and we put that limiter like this Lx and Ln, and how what actually mean. So, equation will be dy by dt is equal to u, same as before earlier also dv by dt u, but here no question of v, it is dy by dt is equal to u and it is Lx, it is Ln. Now, limiting action, that y, if y is lying between your Ln and your Ln and Lx, then dy dt is equal to u. I mean if y is lying between your Ln and Lx, right, then dy by dt is equal to u, this is the constant, right, then it is okay, the derivative is dy dt is equal to u. Now, if y your what you call greater than equal to Lx, that means if y greater than equal to Lx, right, then your what you call that then and dy dt is 0, so both things are there. If y is greater than Lx, and if dy dt, that dy dt is greater than 0 and positive, if y greater than Lx and dy dt greater than 0, then you set dy dt is equal to 0 and y is equal to Lx. So, this is another constant, right. Similarly, if y less than equal to Ln and dy dt less than 0, then set again dy dt 0 and y is equal to Ln. So, this is your non-Windup limits, right. So, this is a symbol, that means when you are using controller and some other things, that what you call, we use your what you call limiter, right. So, different limit that Windup limits and non-Windup limits. So, this is for when integrator is there and this is the condition. Suppose your system deserve this kind of your what you call applications, then accordingly you have to design, right, accordingly you have to design. And you can write code, of course. Nowadays you are putting everything in MATLAB, but at least see that how things are happening if you write code of your own, right. So, this is integrator with non-Windup limits. Now, next is your what you call with Windup limits, the variable v is not limited, right. Therefore, the output variable y cannot come up a limit until v comes within the limit, right. Similarly, with non-Windup limits, the output variable y is limited. It comes up the limit as soon as the input u changes sign, because positive or negative, right. So, now next is the figure C and figure D, will come to that. Show the difference between two types of limits when applied to a single time constant block. The significance of the two types of limit is similar to that for an integrator, right. So, with a Windup limit, the output y cannot come up a limit until v comes within the limit, right. Similarly, with a non-Windup limit, however, the output y comes up the limit as soon as the input u re-enters the range within the limits. That is why all I have underlined. So, representation. So, now it is a first order transfer function, it is a first order transfer function. Earlier it was integrator, now it is a first order transfer function, and input is u and output is v, but restricted that your Lx and Ln, this limit is there and this is y. Now, for this one system equation will be, you can try to write it, that this is dv by dt will be u minus v upon t, this t 1 plus s t, the capital T, right. So, it will be dv by dt will be u minus v by t for this one, it is a first order block diagram, right. Now, limiting action. Now, if v actually lying in between ln and lx, then y is equal to v, same as before, right. Now, if v greater than lx, then y is equal to lx, right, and this is the equation dv by dt is equal to u minus v by t, and if v less than equal to ln, then y is equal to ln, right. So, this way that your what you call limiting action will takes place. So, this is actually single time constant block with Windup limit, this is actually Windup limits, right. Similarly, for this is for non-Windup limits, this Lx and Ln limiter, this is 1 upon 1 plus St, this is u and this is y. So, let us define that f is equal to u minus y by t, u minus y divided by t, right. So, let us define system equation f is equal to u minus y by t, right. Therefore, if you put the limiting action, if y is lying between your ln and lx, right, then dy by dt is equal to f, then your dy by dt will become f, right, if it is lying in between this, right. So, but we are defining f is equal to u minus y by t, right. So, dy dt will be f, that means dy by dt will be this equation u minus y by t, right. Now, if y greater than Lx and f is positive, that is greater than 0, then you set dy dt is equal to 0 and y is equal to Lx, right. So, that is if y greater than equal to Lx and f is positive, right, that is f is equal to this one u minus y by t. And similarly, if y less than equal to ln and f is negative, then again you set dy dt 0 and y will be equal to ln, that means you are restricting this, right. So, I mean when you will design your what you call this kind of limiter for your system, I mean what kind of limiter you want, right, depending on your system. So, this is single time constant block with non-Windup limits. Now, so next is your what you call lead lag, you have studied no lead lag power system stabilizer, but there we have not considered your what you call that your this limits, right, because we wanted to avoid those things for the classroom purpose. So, just representation will show. So, this is 1 plus STA divided by 1 plus STB. Input is u, output is y, and TA less than TB, this time constant TA less than TB, and this is the representation, right. So, this representation will represent this thing like this, physical representation, I mean electronically when you realize it will be like this, I mean this one, this whole thing when you realize electronically it will be like this. So, this is a small exercise for you to do this, right, it is not a difficult one. So, in this case if you look into this, the representation like this, and if this is u, this is TB minus T upon TA, this is 1 upon STA, and this is y, feedback is coming here, a negative feedback is here, and this is Lx ln, and this is your just your Windup limits like this, right. So, only this part you have to take care of, right, and this is your, here it is u, and whatever feedback is going here, right. So, it is like Windup limits, this is Lx and Ln, right. This is you try yourself, right. From there you can make it electronically. If you want to realize this one electronically, you have to design this way, right. So, limiting action will be, now if V is lying in between Ln and Lx, then y is equal to V, right. So, this is V and this is y, right, same as before, and if V greater than Lx, then y is equal to Lx, and if V less than Ln, then y is equal to Ln. So, lead lag function with non-Windup limits, but this expression looks like Windup limits, because we have made the thing simpler, right. So, with a lead lag block, the interpretation of the action of a Windup limit is similar to that of a single time constant block that we have seen before, right. So, with this just what we will do, that this topic, that power system dynamics control and monitoring, is actually closed. Now, question is that right from the beginning, just 2-3 minutes I would like to tell, we have studied the synchronous machine model. It took, I think, if I recall correctly, 14 hours or even little more than 14 hours, right. So, that is actually I have to cut short many things, but tried my best to see that things are meaningful for you, right. Then we have studied, and there in the synchronous machine we have studied your participation factor also, then totally single machine infinite bus model, but multi machine system not possible in a video course. It is very complicated mathematics and lot of derivations are there, which is not possible, right. And that's why we have restricted ourselves to single machine infinite bus. We have studied participation factor, eigenvalue analysis, right, all sort of things we have studied. Then we have studied your transient stability analysis for multi machine system only, right. I think 4 or 5 examples, good examples we have taken. Just when you will go through this course, if you find any error I have made or any calculation errors, just send me a mail. So, I will appreciate that. And then we have studied your automatic generation control in deregulated environment, because initially we started with your what you call in conventional scenario, then deregulated environment. So, certain things we have made it, calculations and other thing, just listen carefully all these things. Perhaps something may not be available, 1 or 2 things may not be available in the book, but when you will listen to the lecture, at that time everything will be what you call explained in the forum, right. So, these things we have studied. After the state estimation also, whatever is possible as far as the classroom exercise is concerned, that way I have tried, right. Otherwise, many cases you need your aids of computer, right. Without the help of computer, you cannot do this, right. And at the last, we have taken little bit of your hydro turbines, although governor model of hydro turbine we did not do, but thermal power plant also modeling we have done it, but for hydro turbine governor model we did not do, but a simplest hydro turbine model we have considered and a simple problem we have considered. And the last, the subsynchronous oscillations, I thought little bit I should cover with the Windup and non-Windup limits, right. With this, hopefully I do believe that it will be useful for you, particularly for postgraduate students, right, as well as those who are teachers in various colleges, right. But question is that this course is highly mathematical. From the beginning you will be knowing that this course is purely mathematical, right. But hope that whatever we have tried, so just have a look, and if you have any comment or anything, you please send me mail, right. Directly you send me email, and I will appreciate that. So, thank you very much, and okay. So, this is the end of this course. So, thank you very much.